everyone. Please welcome today Longhuan Ju. So Longhuan Ju joined the School of Marine Science and Ocean Engineering at UNH in September 2023. He's a research scientist in the Center for Sustainable Seafood Systems, where his primary focus is developing engineering designs and evaluation techniques for coastal and offshore sustainable seafood systems. He has extensive experience in numerical modeling of structural dynamics, fluid structure interaction, regional coastal wave current sediment processes, and flow vegetation interaction for coastal resilience. He holds a bachelor's and master's in naval architecture and ocean engineering, as well as a PhD in civil engineering. So please give him a
Okay, good afternoon, everybody. Do you like the video? I enjoy the music. People correlate.
The sun is shining down, and the waves are crashing all around. Ooh, you know I can be found chilling in this little old town in the middle of the ocean. In the middle of the ocean. In the middle of the ocean. In the middle of the ocean.
Okay, are you relaxed? Good. Now, welcome to the, so I will introduce the music a little bit. So this is middle of the ocean. We know UH is not in the middle of the ocean, but we are in the middle of the world. Now, welcome to the world of aquaculture, the Center for Sustainable Seafood Systems. Our director, Professor David Fredrickson, without him I cannot work. He introduced our researches last semester. So today I will focus on more details about the modeling for Kelp systems, including the structural dynamics and the whale impact and the coastal protection. So we have 4 permitted aquaculture sites. One at near of the UNH Marine Research Complex in Newcastle. That is our integrated machinery for aquaculture located. And the second one is the Saco Science Center that's educational kelp farm we deployed, and I also shows. So we developed deployed 2 kelp farms in IMTA sites and it's LPA sites. I also show that is used the well-safe component. And our objective is to design a new system for the offshore site and also consider the well-safe components. So first one, structural dynamics. I will introduce the Kelp systems first in case some of you may not know this. So the Kelp systems composed of the anchors, the chains, and the moor ropes, the cultivation lines. We also call it the backbone line, and the corner buoy that is used to support the weight of the moorings and one side of the chains, and the support floats that is to the biomass of the kelp. So this is kelp. It looks like that, right? And it moves in the water. So how can we model that? That is very challenging. So our idea is to separate the kelp biomass into many aggregates of kelp. And for each aggregate of kelp, it may consider like being element. Then we can use Morris equations to calculate the drag forces or the hydrodynamic forces on the aggregates of Kelp and then combine them together. Then we can analyze the dynamics of the Kelp farm systems. Now we have the ideas, but we need a bridge to connect the real-world model and the numerical model. We need to know the drag coefficients. How can we do that? No worries. They have the data. He did the full-scale model for the kelp using plastic. And that is 3 meters long, 1 meter wide. And he did in the towing tank to get the drag coefficient. So he did 2 cases. One is a flow that is perpendicular to the mountain tail, and the other one is a flow that is aligned with the mountain tail. And it's told at 5 speeds, 25 centimeters per second, 50 centimeters per second, 75 centimeters, 1 meter per second, and 1.25 meter per second. And we redefined the Reynolds number based on our equivalent models element. So we did an equivalent cylinder such that it has the same length and mass of the aggregate of Kelp. And then we fed its data. Then we found that no matter the flow is perpendicular to the aggregate Kelp or aligned with the Kelp, the relationship between the drag coefficient and the Reynolds number are the same. Then we can use these formulas to do in our model. So firstly, we validate the model for the aggregate of the Kelp. So here is aggregate Kelp with waves. It fails like that. With velocity increases, the angle between the Kelp model and the horizontal line becomes smaller. And our results here, we compared with the angle and also the forces measured at the mountain end of the Kelp. And his results, they look very good. So at this point, maybe someone may say that we are using the fake data and they use the cases to validate your model. How does it work for the real world? So, no worries. Dave has the field data too, so we can use that to validate our model. He did the experiments at the Saco Bay, Maine. He deployed a single line Kelp farms there, and the blue dot is buoys that is positions of the buoy, so we can know how the Kelp long line is deployed. And its rescuer is 80 CP position. So he also made the wave and current conditions that we can use as input for our model. So this system is use ropes as the moon lines and also the cultivation line. That is 1-inch 3-strand nylon. This is 122 meters, and the water depth is 15 meters. And this is almost in. So this is a model setup, and this is a long line here, and this is input current. So we measured the waves and currents at 2 positions, one on the west and one on the east. But we found that the current comes from the west-east. So we use the data from made as the west as input. And the waves comes from the southeast. So we use the wave data on the southeast. And the current, the current is like 50 centimeters per second. And the waves, the case we used is the wave height, the significant wave height is 1.76 meter. and the wave period is 7 seconds. And this is a spectral data we translate it into time series data, so we can drive our model. Here's our simulations. And so current comes from the southwest, so it drags Kelp bend to the southeast. And the waves comes from the southeast, and it makes Kelp zone moves like back, forward and backward. So this is the data comparison. This is the time series of the tensions, the mooring tensions on both sides, west and east side. And here's the red lines and the blue lines is our simulations. And for this part, that's like from us. So we choose the steady part to for the comparison. And the magenta lines and the thinner lines is Maine data. And we also, it looks not too bad, right? And this is our spectrum analysis comparison. So because we, for the waves, that's spectral data. That is not actually the time series data. We transfer the spectral data into time series data. So they are different from the real data. But we assume that the mean value may be similar. So if we look at the comparison for the mean loads, so the difference is like 20%. But considering this is the field work, not the lab experiment work, so there's a lot of uncertainties. And we also did an uncertainties analysis. We found that the areas may increase or decrease. You know, that's the field data. We cannot make it very accurate. So in our application, we usually can use a safety factor to make sure that our design could reach the requirement. Okay, now we have some model. And can we apply this model to design the farms for the offshore side right now? No, not right now. We should consider the whale safety. So, you know the whales. Well, yeah. So I made this slide during Christmas, probably 2 years ago, when I holding my newborn baby, and I have a 2 years old daughter. She likes, listen to Christmas songs like the noodles, Chinese noodles. So I just said, I think this is fun. Kids are born artists and also born teachers. They always teach us things, especially taught me a lot of to say no. I said a lot of no's every day. Although I always said yes at school. Okay, so the whales like kelp, that increase the rates that they would extend entering the kelp farms. And with the ropes, if the rope is lax, the whales may get entangled, especially in the New England area of the North Atlantic right whales. They are endangered. And it was there for only about 300 individuals left, and only 70 reproductive age females among them. So we need to do it right. And the whales cannot talk, but we can talk, right? So, and we learned how to say no. So to use ropes. So in this new design, we replace the ropes by using some whale-safe components. The first major change is the mooring ropes. We propose to use fiberglass wrap. That is can work well for tension, so it can support the systems, and it has a resistance that could break it at a smaller force. And we also replace the backbone, the cultivation line, using the HDPE pipe. So, yeah, and it is hard to wrap. So this is a rod, and that is Michael Chamber. Yeah, he's performing how to break the rod easily. Yeah, but the whale cannot break the rod in that way. And he, for the small, simplest case, it hits a rod and then bends the rod. If there's a movement that could cause the rod so they bend and then break. And for the HDPE pipe, so Dave has a very good example to show that the HDPE pipe may kink, so to avoid the rub of the whale. And also the kelp grows very well on the HDPE pipe. So this case we deployed in last year. Okay, now I will show some our research on the wave impacts with rat, especially the rat. Louis Gilman, a previous master student, did a lot extensive experiments on the rat, including like the 4-point bending test. And he found that if the rat bend with the bending radius is like 20 centimeter, then it will break. Remember that. Then now we'll do a case study. So this is humpback whale, and which it can be like 14 to 17 meters long and up to 50 meters long, and the cruising speed could be like 7.9 kilometers per hour, and it can be up to like 27 kilometers per hour. And yeah, in this case study, which is a length of 10 meters, and then we calculate the weight based on the formula that is like 14 tons. And we assume initial speed like 2.2 meters per second. And in our case study, we consider the whale as a mass point, and the rod as a spring. So with the whales, here's the rod, the whales kinematic energy could transfer into the potential energy of the rod. Then we based on the equation, the energy compositions, then we can calculate the velocities of the whale and the rod and the bending radius, and then we can say if it will break. So this is our simulation. So we found that this is a bending radius of this rod, and when it decreases to the breaking radius, it breaks. And the impact force, that is like 5,000 Newton. Okay. And sometimes Louis also did this experiment for the tensile strength of the rod. It break at like 20,000 pounds, so it can withstand storm event. So in our previous simulation, we didn't consider the fluid yet. So we just consider the whale as a mass point. But we know in the fluid, it's a different story, right? Because of the flow resistance. Right now, I would like to also impact the fluid interaction with the whale. So I recall my PhD study. I developed a model for the wave vegetation interaction. That is also a fluid structure interaction model. So now I'm thinking to transfer the vegetation into whales. Is it possible? Well, it's not possible. It's impossible in the real world, but it's possible in our numerical world. Okay, now magic time. Do you want to see it again? Yeah, so that's so this is immersed boundary method. So we didn't create the whale on the free domain. We just define the boundary conditions for the whale. And then the computational domain is like 80 meter times 20 meter times 20 meter. And for the very fine mesh is like 0.1 meter. Now we'll prescribe the motion of the whale. The frag motion, that is like 2.4 seconds per cycle. And for the flipper, it moves slower, that is 9.6 per cycle. And then this is our simulation. So the whales change the full field. And this one is pressure. So the red color indicates the increase of the pressure. The blue color indicates the decrease of the pressure. So when the frag moves upward, it compresses the fluid, so it increases the pressure, right? So it makes sense. Okay, now because the breaking force for the rod is 5,000 Newton. For this case, the whale motion. So here, the black line is the force generated by the whale. That is a net forward force. So it's considered the thrustful and also the flow resistance. So the average is like 8,000 Newton. That means the whale's potential to break the rod. By the way, so I did the, I showed the way that we transfer the vegetation into the whale just in 1 second, right? But in the real world, I spent my whole spring break to modify the code and then get it work. So maybe next time when Hannah asks me if you can give a seminar after the spring break, maybe I should say, yeah, maybe after summer break, I could get the incomplete result. Okay, right now, this is our model. So how about the real one? Does it work? No? Well, no models are right unless it is validated, right? So how can we validate it? No worries. Dave has the data.
I don't know about this one.
But he didn't share the data right now. So I cannot show the results.
Some are useful, that's what it is.
Okay, we assume our model works. Now we can design the farms for the offshore side. So this is our initial plan, but I will leave it to this Jackson here. Yeah, so I will leave it for Jackson to present in the future because this will be his master thesis. Then I will jump into the wave attenuation part. So if we deploy like huge kelp systems in the ocean, it will reduce the wave energy, and then that could provide protection for our coastlines. This time, it's not numerical model, it's an analytical model. So this is our model. For each line indicates long lines, and the waves comes from the left and then propagate to the right. And we assume that the wave energy dissipation is induced by the work of the drag induced by the kelp. So this is our equation. And when we do a little bit of math, we can get a simple equation for the wave height decay. That is reciprocal to the distance or approximate to the exponential decay with distance. So the KD is the wave height decay coefficient. It looks like that. And the gamma S and gamma C represent the effects of the kelp dynamics. So this is my work, and my PhD study, like several years ago. And so we know this is a model. We have to validate it. How can we validate it? No worries. Well, this time I do the experiments. So yeah, otherwise I cannot live without Dave. So we did the experiments and supported by NEPS lab. And this is when we made the elastic modulus along the lens, it changes a lot. And this is a long-life kelp, and this is our model. We did a downstream model with silicon film, that dynamically similar. And this is the experience for like 20 curtains of blades. That means 20 lines of kelp. And this is our numerical model. So here's the results. The dots is the experiment data, and the lines is our numerical our model. So we found that the EDR is energy dissipation ratio. So that is kind of like the wave energy reduction. And we found that the wave energy decrease with wavelengths. So for shorter waves, the kelp farm could get more wave energy. Yeah, that makes sense because for the inner waves, the wave optical velocity decrease along the depth. So on the surface, the wave energy mainly focus on the surface. So the suspended kelp farm could get more wave energy. And we found that the wave energy did not change too much with the incident wave height. However, the wave energy reduction increases a lot with bait length. And also the D1 is the gap between the water surface and the kelp. So if the kelp farm is more close to the surface, it can get more wave energy. And we also did sensitivity for the elastic modulus of the kelp. We found it has little influence. And we also analyzed the canopy density, so how many blades per meter, and the numbers of long lines that we managed. We found that like 200 long lines with 400 blades per meter with 1 meter long blades that can reduce 47% energy of 6-second waves. We also did a seasonal analysis. So we know the kelp grows a little bit in January, if we deploy it in December, something, and then it grows a lot during the May and June. So we found that the wave energy velocity is the largest when the kelp grows the last. So in this case, we found that 50 long lines with 2 meter long blades can reduce 29% energy of 1 meter high 6-second waves in 8 meter deep water. So because considering the seasonal impacts, we may use like biannual and multiple partial harvesting techniques to keep the wave attenuation capacity of the kelp. And yeah, the previous analysis for the linear waves, but in the real world, that is kind of like random waves. So we also extended that model for random waves, but I don't have time. I don't think I have time to show it here, but you can read my paper. Yeah, published in Coast Engineering. Okay. So in this talk, we introduced the structural model for the kelp systems and the models for the waves and the kelps, and also the wave attenuation capacity of the kelp farms, like for the coastal protection. So our objective is to define kelp farms that has structural integrity that with could stand with storms, and also it's very do not harm to our important resources like the whales, mammals, and also can provide coastal protection to improve the coastal resilience. So that is a way how we embrace our world. Okay, so finally, I would acknowledge our team members. So the first one, Professor David Fredrickson. So he's a huge resource. Without him, I cannot live. And Michael Chambers, who is strong, that can break the rod easily. And Eagle, he's not here. And Michael Doughty, he's also very strong. And Eric, Michael Coogan, myself, our PhD student, and Jackson Prexon. He's a big potato who will design the kelp farms for our offshore site, and Richard. Okay, that's it.
Well, thank you so much for the presentation. You can take any questions you'd like. I have plenty of time.
Or you can call them out, I think it's easier, because I always cause trouble when I'm
Hey, first of all, thank you for the presentation. I found it really interesting. I wanted to ask about, so I know you did do testing with the kelp in the field, but for the lab observations, you made that the 3x1 meter kelp.
Not me,
plastic
Dave.
thing. I'm sorry, Dave. I almost thought you did it. That would have been practically true.
I did a very small one, like 10 centimeters.
Okay, so I guess I was wondering what was the benefit of making like artificial kelp instead of just using like a kelp from a specific species? Because like as you're saying, there's like complexity for the.
Well, ideally, I would like to use a real kelp, but at that time, I don't think we have the models because I think they did an experiment in summer, right? There's no kelp.
Yeah, so real kelp is kind of flimsy, all right? And this was done in a big naval architecture facility. And when you're doing these type of tests, you have extensive replicates. So the actual kelp is just not robust. So we probably did 100+ toes. And so and that model being full scale because of scaling issues, especially with respect to Reynolds number, we want to have the full scale model to match Reynolds number because that's the only way you can do it. We needed a robust model and we needed a dense model. And so that model right there had it was 3 meters long times 178 strips. So what's 3 times 178?
Over right around a little less than 600. Yeah.
So a half a kilometer of plastic was put into that model. So it's really hard to do that with kelp.
Right.
And then get the replicates you need. And so that's what we chose.
I'd also assume that you'd have scaling. If you tried to put it down to a smaller scale,
Either-
you'd have so many problems.
You have so many scaling issues.
Because how would you get it that light? Yeah.
Right.
And for my case, there's another issue because for the kelp we need to use salt water, but in my university, that flume is designed for fresh water, so we cannot use salt water because it may damage the motors. So we have to use the plastic something else to represent the kelp. Yeah, if we have the facilities, we can. Yeah, I prefer to do the use the real kelp, but it's very difficult.
Thank you again. I guess kind of piggybacking off that, this is the second time I've now seen that silicon film, I've seen that used for eelgrass modeling. This is the first time I'm seeing it for kelp. Is that like the ideal material for, I guess, vegetation in a modeling environment, in a lab environment, or?
So I think they're different. So for the eelgrass, the mass density is smaller than the water. And for the kelp, the mass density is larger than the water, so it will sink. And the silicon foam I use, the mass density is larger than the water. So that is why I choose silicon foam material. And also we consider the flexibility. And the kelp is very flexible. We should do the dynamic similarity to in case that our experiment model can represent the real case.
Thank you.
Yeah.
What's the lifespan for the fiberglass lines? Is it
Lifespan.
more, like, how long do they last in the water without?
We don't know.
No, do you have like an anticipated lifespan for them? Would it be longer than rope or?
That's a great question. And so it depends on the type of fiberglass rod that you're using. But we have done experiments where we just keep it in water and then we slice it in half and use microscopes to look at water intrusion. And in some of the fiberglass material, we do see water intrusion. And so we're always on the lookout for different composite components that we can use for that. Yeah, that's a great question.
Would you maintain it in the similar sense of like a sailboat? Would you have divers that would go down and kind of be like cleaning it?
So not necessarily, though you do get biofouling on all your material, just like on the bottom of a sailboat. But a lot of this stuff is in deeper water where we don't have as much biofouling as that surface. The biggest issues with the fiberglass rods are the terminations. So normally when using ropes, you splice the rope, you put a thimble in it, use shackles. Everyone here has done that type of thing. So we spent a lot of time on figuring out how to take these fiberglass rods and putting a termination on it so we can put a shackle on it. And that's the hardest part. And then, go ahead.
Are you talking about like at the surface or at the seabed?
Just like as a part of the mooring component.
Okay.
If you have a mooring rope, you have a splice and a thimble at one end and a splice and a thimble at the other end. And most people know how to splice 3-strand rope. Other types of lathes are harder, but the fiberglass rod, you have to have some type of mechanical connection to the rod. And we spent a lot of time trying to figure that out. Different like epoxies, it's the hardest part of the problem. Yeah. Great question though.
Yeah. That could be a lifelong research.
Oh, how expensive are the fiberglass rods compared to traditional rope?
Okay, I think that's
Sorry.
So those fiberglass, so we rate the fiberglass rods as price per holding capacity. All right, and it's comparable to rope, and that's why we're excited about it.
Oh, okay,
Yeah.
that's really good.
Yeah, so if you take like a 3/8 inch rod and a 3/8 inch, say, 3-strand nylon, it's comparable.
So it's practical for people who actually want to sometime in the future have recreational farms or something like that.
Yeah, the tough thing, and Mike Doherty can talk about this, is deploying it. And then because you can't coil it up because there's a minimum bending radius, or there are breaks. It's hard to manage that on the deck of a vessel. And you've deployed tons of this stuff, Mike D, right?
Mm-hmm. Yeah, you definitely have to adapt your deployment strategy
So
when
then,
working with it.
how deep waters are you looking at these in?
What have you deployed them
Yeah.
in, Mike D?
I forget the depths of the Saco Bay farm, but probably about 50 foot.
Yep. It was
Oh, wow,
yeah.
okay.
And we have a farm right now, or a line out that's in about 50 feet of water out at Appledore.
Wow, okay.
With some of this equipment.
So I want to ask you about wave dissipation. Your simulations were for 6-second waves? Your simulations were with 6-second waves.
For the wave attenuation, yeah.
Yeah. So did you run simulations at other frequencies?
Yes.
And is there a frequency dependence? Because the wavelengths
Yeah,
obviously gonna change.
it's frequency dependent. So the wave attenuation increases with wave frequencies.
Wavelengths get shorter, you dissipate more energy. Is there thoughts about, so if you look at pilings in a bridge or a pier that's sticking out.
Yeah.
And you look at a certain angle and you block all of the waves coming from that angle.
Yeah.
Can you strategically place your kelp forms or whatever you've got out there in such a way to block the waves coming from the most dominant wave direction?
Yeah. Yes, we can. Yeah. I thought you will ask me the oyster farm model. Yeah, probably next time I will show you how to transfer the vegetation to oyster farms.
That's good, thank you.
What you show that the whales have enough force to break those fiberglass cables, but is there anything else that can easily happen and can break those cables? Like how I have no idea in my head how much 5 kilonewtons is underwater. Like what is there anything else that could easily break that mooring? Like a storm, a log? And if it did, sorry, what's the problem of having that those broken fiberglass shards in the water?
If it broke, what happens? So firstly, we hope the fiberglass rod could be strong enough to support the farms, right? And if it breaks, so it may moves away along with the waves and currents. But we have the anchors and mooring lines that can hold it, and also for the other part. So we don't want it to, to make it like a ghost anchor because that is more dangerous.
It's also I'll go ahead, Skip. It's also like the mode of failure, right? And so in environmental conditions like storms, everything's in tension. And as long as the terminations hold to a certain percentage of the capacity of the rod in tension, you're probably okay. And so whales will fail it by forcing it, say, orthogonal or perpendicular or some angle and bend it, provided that you have a strong enough anchor force on the terminations. And it's that bending and the force, that point force on the side and that load case, which is substantially different than environmental load case, that will cause it to bend at the prescribed radius and force. And so that's what he's trying to do, is figure out what that whale force is that creates the bending.
Yeah, well, part of the question was, is there anything else that can create that force, like a log in a strong current? I don't know. I don't have an idea.
Could you just simulate a log in a strong current?
I just mean like because I have no idea.
Or a submarine or something? Submarine good.
Big clippers.
Yeah.
Big clippers.
A diver who's mad at you.
Yeah, it's more of
a
a
lobster fisher.
Yeah, actually.
it's just more of an idea of how often could this happen.
Yeah.
Not what objects can break it, but more how often could this happen.
Good question.
I'm intrigued by the assumptions you make about the collision of the whale with the.
Yeah, that's a very simple assumption. Yeah.
First, whales are pretty intelligent, and I think it's just going to slow down for one thing when they feel an impediment.
Yeah.
So that kind of changes the equation.
Yeah.
And then the second, they swim often with their jaw open, which would mean there'd be two joints.
Yeah.
And I think they would each not be carrying as much weight. And then the probability that that thing would stay on their bullnose, I think is pretty low. And it probably would slide down and either go away or tangle in the fin.
That's what we want the whale can do.
Pardon me?
I mean, if the whale could slow down and then swim away, that's perfect. The whale do not need to break the rod. We're just the worst case that it cannot escape from the system, and it can very easily to break the rod.
And his point about the logs, I'm mooring on moving water, and it gets tangled with huge trees all the time. It's a big issue, depending on where you are.
I should study more about the whales' behaviors.
I have a question about that to follow up. Like, I don't know, but my sense, even from your video, I feel like whales, part of what their propensity for entanglement is that they spin when they think they're caught in something. And I wonder if that wouldn't change the calculus a little bit about how the failure mode.
Actually, I don't know. I don't know how the whale get entangled. We may guess that when he moves through the ropes, because the ropes is very soft, and there's waves and currents that may makes the ropes to move as expected direction, so that could entangle. But we don't know the mechanisms behind that, and we don't have a video of the case, so we just guess and assume, makes assumptions, and.
But if go to the picture that has the lobster pots.
Okay. This one?
Yeah, so here, this is the North Atlantic right whale, and this is the classic problem, right? And so the lobster pot gear is all slack. All right, and the lobster pots themselves make really, really bad anchors.
Yeah.
All right, and so the whale hits it, and it gets caught in its baleen, especially the North Atlantic right whale, which feeds at the surface with its mouth open, and it gets caught. It's slack rope. It gets caught on a body appendage, and then it drags everything along with it. And then in order to get out of it, it starts to spin. And that's what you see on the right-hand side. All right, so what we're trying to do is go after all of these things. So we want to, and so this is, I don't mean to be hijacking the conversation, but I guess I am. So we want to have these modeling tools such that when the mass or the kinetic energy with the propulsion of the whale hits the gear, the anchors hold. By having the anchors hold, we can force breakage into some other part of the component. We remove the rope so we don't get that wrapping effect. We tension everything, so we size the buoyancy such that there's a pre-tension, so it sheds off the animal first. That's what we want to do. But if for some case none of those things happen, we want the rods to be able to snap at the force of the whale only if the anchors hold. So based on this picture, we try to develop our strategy, not knowing what the whale is going to do, in these multiple mitigative efforts.
So also in theory though, even if it didn't snap and the whale just pushed it or
that's
it
the ideal
didn't,
thing.
it would it still wouldn't have that entanglement problem happening because they're not now able to pull. In theory, everything's not on a slack line and they're able to slack it up and wrap it around themselves.
Strong bending resistance.
Right.
So it's not going to wrap. It's going to break before it wraps. And it's pretension. So we want all the gear to shed off the whale beforehand. But if it does somehow get caught in a baleen or something like that, and it can't, it can generate the force to snap it if the anchors hold in that mode. But then the gear also has to be able to withstand offshore, northeast storms. So those are all that's the entire set of design criteria that he's literally tackling all these things.
I don't know.
You just ask the question.
We also have some online questions, so.
Oh, no, you're fine.
I don't know if you wanna address the ones in the room first, and then it's also workshop, so.
Let's do one online. I think we're running out of time. First question is from Louis.
Yeah, his unit.
When you were modeling a farm and you get a month or two of ADCP data, do you do anything to expound that over longer time periods? Is this a time series analysis task like Dr. Lippin takes?
So in this case, we just select a period of time series of the data and then do the validation.
From Gordon King, what happens to loading on the farm structures with extreme storms? And can the farm be built strong enough to survive these extreme events? Cool. Have there been accounts of whales getting tangled in gear well anchored at both ends and under tension? Have there been accounts of whales getting tangled in gear well anchored at both ends and under tension?
The anchor both ends and not in tension.
Rather than these surface buoys that just have the traps at the one end.
We can solve the problem with the lobster pot being a poor anchor, except it's not but it's still like flexible in the way that a rope would be. I think that's the question, right? Has that ever happened to a whale? I think is what it's as far as
that's how you guys are doing this.
You looking at me? I'm half deaf, so I can't hear anything. And that's not a joke. I'm literally half deaf.
It's always hard to answer a question that goes, has this ever happened to a whale?
Yeah.
Well, that's why he said it counts, right? Because it's like,
Not that I've ever heard.
yeah, none of the whales I know.
I was gonna say none of the whales I know. Well, I've read a fair amount of different aquaculture, farm-related interactions and fishing-related interactions with whales on, from global publications. And usually there's some component that is loose. It's an undone end, or the whale coming into contact causes one end to break. I don't think any of the documented interactions occur when nothing is broken, at least in terms of just a line situation. And in terms of a real entanglement, there's other interactions, but I don't think the entanglements have really been documented unless something is actually broke. Is my read on things so far.
Thank you.
All right. Well, I think that's enough questions.